dilutions. And we said last week, I showed you this trick last week. Let's say you have a stock solution, stock of 100 millimolar, and you want 10 milliliter of 1 millimolar solution. And I showed you this trick with this, the doctor wants, and the pharmacist has. So doctor times doctor divided by the pharmacist. So the doctor says, I want 10 milliliter of 1 millimolar solution, and the pharmacist says, I'm terribly sorry, we only have 100 millimolar solution. So how many milliliter do we need for that? Well, the millimolar cancels out, and we have 10 milliliter divided by 100, and this gives a 0.1 milliliter of the stock solution. So I need, let's put it back here, I need 0.1 milliliter of stock plus, and we make up the rest with water or buffer or something like that, plus 9.9 milliliter of water. And I really want you to remember this doctor times doctor divided by pharmacist. You might not want to write it on exam papers because it looks a little bit weird. But you know, as a sort of a mnemonic, this is certainly good for you guys. Do you work with mnemonics? Do you know what a mnemonic is? It is, mnemonic is something that you can easily remember. Yeah? Have you done nucleotides? Adenine, guanine, yeah? Do you know a really good mnemonic for that? No, it's not alcohol. It is adenine. Is it a guanine or is it a purine or pyrimidine? Purine? How do you know? I pause that here. You have been asked, for example, to do a 1 in 50 dilution with your whatever it was. So, how does that work? Let's always, if in doubt, draw a little diagram. So here you have your stock solution. And here you have your diluted solution. Sorry. Diluted solution. And let's say you take 1 milliliter of that and put that into 49 milliliter. Yeah? That's something that's very common. And you say you started with 100 millimolar solution here. That's your stock. So what is your concentration over here? Concentration of your diluted solution. What is this? First of all, what's the total volume of your diluted? It is 50 milliliter, because you've got 1 of the stock plus 49, so we have 50 milliliter. Now this would be typically a 1 in 50 dilution. 1 that's this guy here, in a total of 50. So this here, the 50, gives you the total. Sometimes it's also written as 1 in 50 dilution. Okay? Happy with that? So how do we address this problem? We could, of course, calculate how many mole we have in here and then divide by the volume. As we've done last week in the last example where we had these different concentrations mixed together. Or we could try, for a change, to be clever. So what do we have? We have 100 millimolar stock. We have 1 milliliter, and we put that in a total of 50 milliliter. Yeah, that is what we have. And we are looking for concentration. What is our concentration of the diluted stuff? What is the unit of concentration? Loud? Molar. Yes. Now, in this case here, we already have a unit there because we have millimolar. Yeah? So, we can say we are looking for millimole per liter. Or we can do it with mole, doesn't matter. Do we have millimole per liter somewhere? Yeah? So yes, we have the 100 millimole per liter. And from this, we take 1 milliliter and we put that into 50 milliliter. What do you see here? This bit here, that is basically 1 milliliter in 50 milliliters. Yeah? This part here. 1 milliliter in 50 milliliters. That's our dilution. That's also our dilution factor. Some people call it dilution factor. Well, now let's see what this turns out to be. We have 100 millimolar per liter times 1 divided by 50. So 100 divided by 50 is, thank you. So it's 2, the milliliters cancelled out. So our concentration is now 2 millimole per liter, or 2 millimolar. That's our concentration when we do a 1 milliliter and put that in 50. Simples. Here's one for you guys. I have a stock of 250 millimolar I take 0.3 milliliter and put that into 99.7 milliliter of water. Okay? What is my final concentration? Okay, so what are we looking for? Well, our concentration, we have millimole or millimolar. Let's just write it down like millimolar. We are looking for the millimolar, that's the concentration. Do we have anything with millimolar in it? Yeah, of course we have. So we have 250 millimolar. We take 0.3 milliliter. And we have that in a total volume of 100 milliliter. Okay? Yeah? So, all we need to do is, our milliliters cancel, and we have 250 millimolar times 0.3 divided by 100. Because we've got 100 milliliter, a total. And this gives 0.75, what? Millimolar. Yeah? You got that? Give yourself a pat on the back. Or ask somebody else to do it. Okay? You're happy with that approach? Oh, by the way, what you've used here again is dimensional analysis. It's quite useful, this stuff. Yeah? Now, let me now come to a little bit more biology. And let's discuss why life is so much easier when you are a prokaryote. So, a prokaryote here we've got, say, E. coli or something like that. And actually, let's assume this E. coli cell has one piece of DNA, which is probably pretty true, that it has just one DNA. Not like humans, not like other eukaryotes. And I want to know, actually, what is the concentration of the DNA in a prokaryotic cell? What is the concentration of the DNA molecule in a prokaryotic cell? Any ideas how we could address that? Sorry? Oh, we need the volume of the cell. That's a very, very good approach. Let's assume, just for simplicity, that our E. coli cell is not the way I drew it. Let's assume our E. coli cell is a cube. Makes it easier. Makes it easier to calculate. How big are prokaryotic cells? You've done that? Between? Sorry? Say loud again.
0 to 10.
0 to 10. Well, the 0 is a little bit dodgy. Let's say 1 to 10. What? Micron. Okay, let's go for 5. Yeah, it's a good size. So we have 5 micrometer. And 5 micrometer and 5 micrometer. Okay? So we have basically 5 micrometer cubes. Okay, so can we calculate the volume of our cell? So we have, yeah, loud?
125.
So we have 5, yes, you are right. 5 times, what is micro? 10 to the minus 6. 5 times 10 to the minus 6 meters cubed. Yeah? Can we do that? Tiffany already said 5 cubed is 125 times 10 to the minus 6 cubed. What is that? 10 to the minus 6 times 10 to the minus 6 times 10 to the minus 6. It is exactly 10 to the minus 18 meter cubic. Okay? So that is in cubic meters. 125 times 10 to the minus 18 cubic meters. But actually we want it in liters, the volume. Because our concentration is always in liters, not in cubic meters. So we need one more information for that. And how many liters are in 1 cubic meter? 1,000, exactly. So we've got 1,000 liters in 1 cubic meter. Okay? So these are all very useful, information. Okay. So I'm running out of space. Let's say we have 1 molecule per cell. The cell volume is 125 times 10 to the minus 18 cubic meters. We have 1 times 10 to the 3 liters per cubic meter. And, of course, we have 6.022 molecules per mole. Right? That's the Avogadro number. And now we want to calculate what is our concentration of this 1 molecule of DNA. That's a 3. This one here doesn't look much better. Look, personal service. Ha! Okay, so can we calculate from this information what is our concentration? Do you want to try it yourself? It's all the information that you have. Give it a go. Let's see what you got. Okay, what is the unit that we are looking for? What is the unit that we are looking for? We are looking for the concentration. Loud? Molar, yes. So that would be moles over liter, exactly. So moles per liter. Do we have anywhere the unit mole? Where? We've got it here, right? But mole is down. Oh, it doesn't matter. We just turn it upside down. So we have mole. 6.022 times 10 to the 23 molecules. Yeah? Now we need to get rid of the molecules. We know that we have exactly 1 molecule per cell. Okay? So the molecules cancels out. What else do we know? Now we have the cell down here. Well, we know that a cell has a volume of 1.28, it's 125 times 10 to the minus 18 cubic meters. And we can say 125 times 10 to the minus 18 cubic meter per cell. So we put the cell up here. 125 times 10 to the minus 18 meter cubic. Yeah, are you still with me? So the cells cancel out. And we know that we have in 1 cubic meter, we have 1,000 liters. Yeah? So the meters cubic cancel out. Are you happy with that? Yeah. So what do we have left in terms of units? We have mole and liters. What did we want? Moles per liter. Hey, yeah! We are on the right track, aren't we? So all we need to do is, we have 1 divided by 6.022 times 10 to the 23 times 125 times 10 to the minus 18 times 1,000. And the unit would be mole per liter. Sorry? And, do you get anything? Yeah, you put them all together. What did I get? Do you get anything? Sorry? Aha! So we get, if you do this calculation, you get 1.3 times 10 to the minus 11, is that right? Mole per liter. Yeah? Or you can write that in a different form. Do you get that? 1.3 times 10 to the minus 11? Yeah? Or you can write this also as 13 times 10 to the minus 12 molar. What is 10 to the minus 12? Pico, yes. Exactly. So that is 13 picomolar. That's the concentration of one DNA molecule in a prokaryote. And it can be DNA, it can be something else. One molecule in a prokaryotic cell is roughly 13 picomolar. Who gives a flying whatever? Right? Who cares if it is 13 picomolar or God knows what? Okay, here comes the trick. Let's do exactly the same for a eukaryotic cell. And again, let's assume that our eukaryotic cell is cubed. Could be an epithelial cell or something like that. How big is a eukaryotic cell? Between 10 and 100 microns. Yeah? Let's go for 50. Okay? Now let's calculate the volume of a eukaryotic cell. So it's 50 times 10 to the minus 6. Cubed again. Yeah? 50 times 10 to the minus 6. Can we do that? Yeah? What does that give us? Do you agree? 125 times 10 to the minus 15 cubic meters. Do you get that, roughly? Yeah? Now that's the only difference between the prokaryotic and the eukaryotic cell. We still have 1,000 liters to a cubic meter. So we could really do you have this sometimes that you hear, music or voices in your head? I'm just worried what happens when the voices go away. So this is the only difference between the pro and the eukaryotic cell. The prokaryotic cell had 10 to the minus 18. The eukaryotic cell had 10 to the minus 15. Yeah? So can we now calculate that for the concentration for the eukaryotic cell. Again, we have mole per liter. We have 1 over 6.022 times 10 to the 23 molecules per mole. We have 1 molecule per cell. We have cell has 125 times 10 to the minus 15 cubic meters, and 1 cubic meter has 1,000 liters. These cancel out, these cancel out. It's exactly the same calculation that we've done before. Yeah? Just with a slightly different volume here. What do you get when you do this calculation? Thank you. So the concentration is 1.3 times 10 to the minus 14. What? Moles per liter? Yep. Molar. And I can write this also as 13 times 10 to the minus 15 molar. What is 10 to the minus 15? Femto. So this is 13 femtomolar. Or in other words, one molecule in a prokaryote is 13 picomolar, and in a eukaryote it's 13 femtomolar. What's the difference? What factor? It is a factor of 1,000 is the difference. Yeah? Factor of 1,000 different concentration. What are the implications for that? Imagine DNA. And you need a protein that binds to the DNA. In a prokaryote, the concentration of the DNA is 13 picomolar. But in a eukaryote, the DNA is 1,000 times more diluted. So actually, the protein has to find the DNA. In a prokaryote, it's easy. It just whizzes around the protein, and sooner or later it will bump into the DNA. But in a eukaryotic cell, the protein has to take much longer because the DNA is far more dilute. It's 1,000-fold more dilute. It's very unlikely that the protein will bump into that because it's so dilute. You can imagine, let's imagine we've got 1,000 people here. So then, for me, it would be very easy to bump into at least one of the people. That easy. And now, I take 999 out, I dilute the people in the room, and I've got only one person in the room. I'm just walking around randomly. It it would be very rare that I bump into that person, wouldn't it? So, as a prokaryote, it's much easier to design your proteins and to design your mechanisms, because even with one molecule has a far higher concentration in a prokaryotic cell than the same molecule in a eukaryotic cell. Now, the eukaryotic cell can do something about that. What can the eukaryotic cell do? Of course, it can develop proteins that bind, that grab, that hold on to proteins, to DNA molecules or other molecules very tightly. Yeah? That's one way. And therefore, very often you will find that the proteins in eukaryotic cells bind much more tight to whatever they should bind. The other thing is that a eukaryotic cell, what a eukaryotic cell can do is it can make its volume much smaller. How can it do that? It uses compartments. Exactly. Yeah? So, in a eukaryotic cell, you've got a nucleus. Now, this nucleus is much smaller than the cell. It's probably the size of a prokaryotic cell. Yeah? And therefore, if you've got your DNA molecule in that, the concentration of the DNA molecule in the nucleus is similar to the prokaryote. So by using compartments, the cell reduces the volume, the overall volume. And therefore, if the volume is reduced, the concentration of what you're looking for goes up. So that's a very, very clever trick. And if your cells get bigger and bigger, you would want to have more and more compartments. And that was sort of the absolutely fascinating invention of life. When prokaryotes got too big, they had to introduce compartments. There was no other way around that, because otherwise the concentration would have gone down too much. So that's what life is all about. Does that make sense? What I will do is